Hi, everyone. I want to continue our discussion about the development of quantum theory with after Schrodinger's equation was developed, the solutions to Schrodinger's equation are known as the quantum numbers. If we recall from Schrodinger's equation, he proposed that the best we can do is to calculate the probability of finding an electron with a quantized amount of energy at some location in the atom. His equation that he came up with produces these things called wave functions, which is represented by the Greek letter psi. And a wave function represents a 3D wave. And that three-dimensional region of space where you are likely to find an electron at that energy level is what we now call an orbital. So you may be more familiar with that word orbital in reference to atoms and electrons. The orbitals of an atom are where, again, the electrons are likely to be found. And we have three integers, three quantum numbers that are going to tell us the size, the shape, and their orientation in three-dimensional space. These are illustrations of some of the first orbitals based on using these three numbers, these three quantum numbers together. And we'll talk about what these shapes represent and how we organize all of this information, because three solutions to describing where one electron is, not to mention there is actually a fourth quantum number that describes the electron itself in that region of space. It's a lot to keep track of. So again, quantum numbers, there are four of them. We're going to go through each one. Maybe not spin quantum numbers so much right now. That will really be more applicable when we start writing what are called electron configurations. But just to learn about orbitals, we're going to talk about principal quantum number, the angular momentum quantum number, and the magnetic quantum number. So thinking about that principal quantum number, this is the energy. This is that energy level of an electron. This is very much like what Niels Bohr proposed when he said there are these discrete energy levels. So the symbol for the principal quantum number that we use is just the letter N, similar to what Bohr used. And the principal quantum number, again, describes the energy of the orbital and any electrons in that orbital. Okay, energy of the orbital. What values, what actual numbers, because remember, these are truly integer numbers. What numbers are allowed for the principal quantum number? You can have any value from n equals 1 up to infinity. You cannot have an energy, a principal quantum number of 0. That value is not allowed. The values start at 1 and then go up by integers, 1, 2, 3, 4, and 5, and so on. Sometimes we refer to the principal quantum number as the shell. What shell is the electron in? Is it in shell 1, shell 2, shell 3? Sometimes we say the shell instead of the energy level. Okay. All right, next quantum number. Actually, I'm going to give myself a little more room here. Angular momentum quantum number. This describes the shape of the orbital. Remember, the orbital is the wave function. It is the three-dimensional region of space, okay? And they have shapes, all right? So there's an energy level where it can be found, right? And then there is this angular momentum quantum number, which is symbolized with a cursive lowercase l, okay? cursive lowercase l. And as I said, it's going to give us the shape of the orbital that we're talking about. And the allowed number values for angular momentum, quantum number. L can be any value from 0 up to n minus 1. What energy level are you at? Subtract 1 from that number of energy level, and that will be the highest L value that is allowed mathematically as a solution to the Schrodinger equation. Okay? So, we sometimes refer to the angular momentum quantum number, right, which is the shape of the orbital, as the subshell. What subshell are the electrons in that I'm studying in the atom? What subshell are they in? And we actually do not use the numeric value of L to talk about the subshell. We use a letter to describe which subshell we're speaking of, at least for the first several subshells. So when L is a value of 0, when that's one of the values allowed for the orbital that we are looking at, that is a letter designation S. Those are S orbitals. Let me write the numbers here and then we'll look at the images of the orbitals. When L is a value of 1, the orbitals, the subshells that we're talking about, are called p orbitals. When L is 2, the orbitals that we're talking about, the subshell orbitals that we're talking about, are what are described as d orbitals. And when L is 3, we're talking about what are known as f orbitals. And then if you keep going in number, again, you can go up to n minus 1. We tend to just now follow the alphabet, with the exception of, I think, letter I. I don't think we actually name any of the orbitals letter I, because I gets used for other things. But G, H, J, K, L, M, N, you would just keep going. These, S, P, D, F, are by far the most common. These are the ones you need to recognize. So let's talk about what their shapes are. The images of their shapes are, for my in-class students, I print these out so that you can have them as a visual. But let's look at them in this set of PowerPoint slides. S orbitals have a spherical shape. It's not actually why it's called S, but it kind of works out nice. S orbitals, all S orbitals, whether they're at the 1 level, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, are this shape. L or P, L equals 1 or P orbitals are kind of a, we call it a dumbbell shape. It's like 2 bars, 2 halves of a dumbbell. D orbitals have this 4-leaf clover shape. And F orbitals, well, we don't really have a great name for this. I call them balloon animals because it looks like you took a bunch of balloons and started tying them together. Okay. All right. L tells you what shape orbital you're dealing with at that energy level. And only certain values are allowed, yes? And we sometimes call this the subshell. You have shell and then subshell. Third number that describes an orbital, okay, is the magnetic quantum number. And we symbolize this with an M, and then we put an L as a subscript after it. So sometimes we say this M sub L, talking about the magnetic quantum number, m sub L. This number is going to specify the orientation of our orbital. So you have to think, yes, when we're talking about in 3 dimensions, okay, what kind of coordinate system are we most used to using in 3 dimensions? There's a couple versions of it, but the one we're most used to using is X, Y, and then a Z, that 3rd dimension coming out at you, yeah? So again, the m sub L number value will tell us the orientation of the orbital on an X, Y, Z coordinate system. Maybe you know this as a Cartesian coordinate system. That's what this is known when it's X, Y, Z. It's called a Cartesian coordinate system. Okay. What kind of values are allowed? M sub L allowed values are all values are allowed for a particular subshell from L up to negative L. We'll do it this way, from negative L up to positive L by integers. No halves, no 0.33s, -1, -2, -3, +1, +2, +3 by integers, okay? Including the number 0 can be an allowed value of m sub L. What this really tells us is the more useful, at least in Gen Chem 1, is this is going to tell us the number of allowed m sub L values is going to directly correspond the number of orbitals at that subshell, for that subshell. Number of orbitals for that subshell. Let me show you what I mean. Let's say you have an L value of 1, 0, which corresponds to an s orbital, right? That's what we call it. What m sub L values are allowed? Okay. We have an n value, that's some number. We have an L value equals 0. What m sub L value is the only numeric value that is allowed mathematically solving the Schrodinger equation, following this guideline, following this rule? The only number allowed is 0, a mathematical answer of 0. From negative L up to positive L, that's a 0. How many answers do we have? How many possible m sub L values do we have for an s orbital? There's only one m sub L value allowed. So there is only one orientation of an s orbital ever. There's only one, and it's the sphere. And it looks like this. In a 3-dimensional system, is there any other way to have a sphere oriented that would be different from any other way? No. A sphere is a sphere is a sphere. So let's think about the next orbital that we have. That was S. Let's think about when L equals 1. And we're talking about p orbitals. When L is 1, We're talking about p orbitals. We've already discussed what that shape is. It's what we call a dumbbell shape. What m sub L values are allowed when L has a value of 1. You have values allowed from negative L up to positive L. -1, 0, and +1. 3 different numbers. 3 different numerical solutions are allowed. That means there are 3 orientations of p orbitals. Anytime you have a p subshell, there will be 3 p orbitals in these 3 orientations. One of them is aligned along the x-axis. One of them is aligned along the y-axis. One of them is aligned along the z-axis. Do you need to be able to sketch which one is going which way? Probably not, but you know, if you're thinking about your 3D system, you have to understand that all 3 of these orbitals, the p, I'll call this x, I'll call this y, and I'll call this z, okay? These 3 regions of space are all there, are all probable, they're all described at the same time. The Schrodinger equation is describing all 3 of these as possibilities at the same time. Okay. They're all 3 right there around the axis, the center point. Okay. They're all 3 there. They exist simultaneously. What else is existing simultaneously at the same time as these other ones? There's some little sphere right here in the middle too. Okay. Gets weird. Quantum theory gets weird. What if you have LS2? I'm talking about d orbitals. What m sub L values are allowed? From negative L up to positive L. -2, -1, 0, +1, +2. How many d orbitals does that mean you will always find? You will always find 5 distinct d orbitals, all 5 having a different orientation, all 5 existing at the same time as soon as a d orbital is allowed. They're all there. Let's look at those d orbitals. Again, I said there are 5 of them, right? 1, 2, 3, 4, 5. We may come back and look at some of these, but let's find. Okay. Again, I told you there's 3 orientations of the p orbitals: px, py, pz. It's not really important at this point that you label these individually so much as an x, y, z, but you should know that the 3 are on the x, on the y, and on the z axes. Okay, here's our d orbitals. We have a what's known as a dyz orbital, where the regions of space are in between the y and the z axes. You are not expected for my class to be able to draw these, sketch these, probably even at this point really use the individual designation. But you do need to recognize that there are 5. Okay, there's the xy, where the regions are in between the x and the y axes. dxz. There's a dx squared minus y squared, where the regions are actually along, not in between, but along the x and the y axes. And then there's this one, which is always kind of fun, a dz squared. It has what we call the donut around it. It doesn't look like a 4-leaf clover. but it is a d orbital. It's kind of the unique d orbital. Okay. And then again, remember all 5 of these are registered at the same time. F orbitals, when you see how many M values are allowed, -3, that's 7 orbitals. Once you have F orbitals, there are 7 different orientations possible. These you will not need to distinguish from here from my class any of the specific names or draw them or sketch them, but they are quite more complicated. And orbitals only get more complicated the higher you go in both shell energy level, the higher your subshell value gets, because you just have more and more magnetic quantum numbers, more orientations allowed. So we will think with that, right, over orbitals, different shapes, different names that we use, SPD. If I'm talking about orbitals that are allowed and not allowed, you may find it helpful to refer to a chart such as this that starts with the very first energy level, n equals 1, very first shell, and shows you exactly what L value is allowed and what M sub L values are allowed. And that's going to help us name these orbitals by both energy level and letter. And then eventually this will help us understand how many electrons can fill those orbitals, because there's an order to that as well. Okay.